Hello, this is the Target 1 assessment for week 6 in physical science, physics semester 2. So this is about a skateboarder, and on the question below, there are two questions that this person is asking, or it would be me, and it asks, the first question is asking, does the mass of the skateboarder affect their speed at the bottom of the half pipe? So our objective for this assessment is to create two hypotheses, or two different versions of a hypothesis for each question. So the first question is does mass of the skateboard affect does the mass of the skateboard affect their speed at the bottom of the half pipe? Meaning if there's a greater, like, would the mass affect how fast the skateboarder would go? So in order to think about that, you have to think about how objects move. So let's just say there's two different kinds of, like, there's an object going down a hill. It's basically what it's doing is it's changing from its potential energy into kinetic energy. It's just transferring the energy. It's not going away or being created. It's just yeah, that our energy was already there. It was already created in the first place, and so it's been transferred from potential to kinetic. So that means that these two must be the same because they are eventually, the potential turns to zero and the kinetic turns to that whatever it was at the very beginning for the potential amount. So that means that they must be equal. So we can set these two to equal, and the formula for the potential would be mass times the gravity times the height, and then the formula for kinetic energy would be 1/2 times the mass times the velocity squared. Well, there's a I should fix that too. So in order to there's a way you can simplify this, and basically what you do is you just divide both sides by m. This is just a simple math property. So this is simplifies to gravity times the height is equal to 1/2 times the mass. No, not mass. 1/2 times the velocity squared, and that's simplifying the equation. So if you take a look at this new simplified equation, there's no mass in there. It's just gravity, height, and velocity. So that means that mass doesn't apply to this situation. So if you have somebody with their different mass, I predicted, and for the hypothesis, that it shouldn't matter what kind of mass you have. Like whether you have a larger mass or a smaller mass, for the skateboarder, it should be the same. And for the second question asks, how does the presence of friction affect my answer? So the presence of friction would be the just thinking about this logically. If we had a skateboarder, let's just make a real quick skateboard here. So very simple drawing, and he's riding right here, and he's going on, let's just say, some gravel. It'd be like like something like that. It's gonna be more. It's gonna have to go through those bumps, and that would mean that there's a it's gonna slow the skateboard down because it's going against it. The force of the friction is going against the skateboard, and therefore it's slowing down. So it's gonna go slower. But if this same exact skateboarder, let's just erase these, if it was going on a smooth amount of something like this, going like that, and then we'll just make some more jump or something, it's going to go smoothly down here, and therefore there's going to be less friction, meaning it's going to go faster because there's less opposition, like less of a force to slow the thing down and make it not go quite as have much as an acceleration, or no, sorry, a greater velocity, not an acceleration, a greater velocity. So it would have a greater velocity if there is a less of a friction. So that's my hypothesis for the second question, because that's just thinking about the different terrains and different ways that skateboard could go down a certain path. So the other second part to this part is to this question, this assessment, is to do the simulation. So I already have it up over here, and what we're gonna try to do is you can just drag them around, and we can see what the mass, how the mass will be affected. So I'm just gonna reset him to default setting of normal speed. So if you click on speed, you can see this is just a rough representation. So if you drag him over to here, and we have to be careful to make the height the same, because if we look at this equation, the height should make the difference. The height right here can impact it. So we got to leave that variable the same. So if we leave him at the top of this area, and then we're gonna let go and see how the how fast he goes by the time he reaches the halfway point of this half pipe. So he's going down here, and then let's just pause this, put in slow motion, slowing down. Oh, there we go. Okay. All right. So we can fast forward till that point. All right, that's where he reaches the bottom. So if we measure this, it should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Hang on a second. 2, 4, 6, 8, 9, 10. So it should be around 10. Around 10 for speed. They don't tell you what kind of measurement, just 10 speed. And then we can try to make the mass larger. So that's what it was, 10 speed. Average, we can just say middle, or mass of the middle, speed of 10. Alright, and then we can write down a mass of large. So we can try out his version of the stunt. So he's going down here, and then fast forward until there. Check out the speed. This should be a speed of 1, 2, 3, 4, 5. It's 10. Speed of 10. So this is looking like the hypothesis is correct, because both of them have a speed of 10, both in mass of a middle, an average mass, and a mass of a larger mass are both 10. So that means that they are equal. So how about a mass of a smaller individual, or smaller skateboarder guy? So we can reset this, and make them smaller, and try them out. Again, at the same exact height. So he's going on here. And we better pause it. Alright, and then the speed. You can just measure this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, relatively, they're around the same exact amount of 10. Obviously, they could be a little different because the height's a little different for each time, but it was relatively the same. So that means that the 10 is consistent through all three of the masses, and that means that all these masses, the mass doesn't impact the amount. So that means the hypothesis must be correct. Alright, so we can check out this. The second thing that we're supposed to do is look at the friction. So there's this friction tab here. So we can click on that. And so how we just have this average, just to see how it turns out, just to watch him go. Like, woo! Alright, so we can check out the speed. Maybe we should reset this. There we go. There, we should make it about, that looks good. So you can show the speed, pause this. By the time he reaches that middle part, it's about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A speed of 10. And then after the second time, he reaches a speed of about, this is just the second time of the same exact friction level, about 1, 2, 3, 4, 5, 6, 7, 8. So it goes from 10 to 8. So we can just record this down. Friction of average, or how about middle, just to make it consistent. A friction of the middle it goes from 10 to 8. So how about we make the friction larger? Oops, we gotta make this mass consistent. Reset skater. Increase the friction. Lots of friction. Alright, so reset the skater. Alright, so there's a lot. Friction middle has 10 to 8. Friction of lots should be. You can watch this and see how it turns out. Alright, I'm gonna record that speed again. Goes from 1, 2, 3, 4, 5, 6, 7, 8, 9. A speed of 9. It's slowing down, which makes sense because there's more friction. But we have to figure out to see if that's really the case. that's the objective here. So it goes from a 9 to 1, 2, 3, 4, 5. Whoops. 1, 2, 3, 4, 5, 6, 7. From a 9 to a 7. So let's look at this data. It goes from 10 to 8 to 9 to 7. This is the greater speed because there is a nil friction, while with lots of friction, you only go from speed from 9 to 7, right, opposed to a 10 to 8. So that just means that there's a greater speed when there's less friction involved, which is making sense from the hypothesis. It looks more probable for the hypothesis. So how we just try non-friction, just completely no friction at all. So we can try him out and see how it turns out. Alright, so we turn on the speed. I'll wait for him to get through the middle. Speed of alright, so the friction for none. So that starts from let's clean this up a little bit. Goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Goes from a speed of 10. And then play again. And then he's going to go to that. Oh wow, he goes a lot higher as well. And then the second time it comes down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means he has the same exact same exact speed. So looking at this data from these three, it goes from 10 to 8 to 9 to 7 to 10 to 10, meaning if there's middle friction, there's a good speed. If there's a lot of friction, it's a slower speed. If there's no friction, it goes even faster than middle speed because there is no friction at all. So this means that the friction actually slows down the object, kind of and that makes sense because of our illustration here with our skateboard. So as the friction is increased, concluding about that, as the friction increases, the speed slows down. But if the friction decreases, then the speed will actually increase. The speed will actually get faster because there's less resistance. So that's the analysis for these two questions. And that means that the two hypothesis must be correct. The two hypotheses must be correct because the mass is cancels out from these two from the equation, and also from logically thinking about the world around us for certain terrains. As it goes through the friction, it slows down. So if there's less friction, the object must go faster, and if there's more friction, the object must slow down. So that concludes this analysis of this experiment.